Hi, everyone. My name is Brandon Rodriguez, and I work at NASA's Jet Propulsion Laboratory in Pasadena, California, in the Education Department. I'm very excited to share some uh, really new and fun topics with you guys because for so long we've been talking about Mars, and of course, there's a lot of excitement coming up with the Perseverance landing on February 18th. But sometimes we forget about all the really exciting missions taking place at NASA looking downward instead of looking out into space, looking at ourselves and our planet and our planet. So to that end, we're going to be joined today by Annie Richardson, who's worked in Earth public outreach and engagement for many, many years, and is actually finishing up her illustrious career with us. So we're really, really excited to hear from her. Before I turn it over to hear a little bit about her work and some of the Earth missions that have been going on for the last few years, I want to remind you guys that at the end, we'll also take a look at some educational resources, how we can take this topic and add that context to your perhaps classroom or projects at home or just your general interest. If you're someone who's asking yourself, how can I protect this planet? Where does engineering and earth science kind of overlap? We have those resources for you guys. So I'm really excited to hear from Annie, and then we'll kind of close out with some Q&A from all of you guys. So if you haven't registered, please do so now. You can ask questions online, and then we'll kind of talk about some educational resources so that you can keep going with this and you can make earth science part of your daily life as well. So with that, let me turn it over to Annie, who's going to share some of her work with us. And thank you so much for joining us today.
Hey, good afternoon, everyone. I am really excited because, as Brandon said, this is my last week at JPL after 43 and a half years hanging around Earth. And I love our planet. And I always ask people, students especially, what's your favorite planet? And when they tell me Mars and Jupiter and Saturn, I say, you might love Mars and Jupiter and Saturn, but they don't love you back. Earth loves you. Earth has the right atmosphere. Earth has this nice ground. It has beautiful greenery, forests, and trees for you. And it has some really good water for us. So I always leave people saying that now Earth is their favorite planet, and whatever they said initially was second favorite. So today I'm just going to talk a little bit about the Sentinel-6 Michael Freilich mission and its predecessors, because it is the fourth or fifth in a series of radar altimeters. So we'll just look at the satellite altimetry, the beginning. So that's my slide number 2. And so we first used satellite altimetry on the CSAT satellite. It was 1978. And CSAT was basically, it was an experimental oceanography satellite. It had a complement of 5 different sensors on it, and one of which was a radar altimeter to measure sea surface height. CSAT only lasted for 90 days, I think, and there was some massive short circuit. But the oceanographer said that CSAT, in its 90-day mission, maybe it was 100 days, it did more for oceanography than had been done in the previous 100 years of ship-going measurements. So we are excited. I was around for CSAT. That was the very first launch I saw as a JPL employee. But the altimeter on CSAT was the basis for the Topex Poseidon altimeter. So we'll go to slide 3 and look at Topex Poseidon, which was launched in 1992. And it had the same type of radar altimeter on there. It had a microwave radiometer. The radiometer is used to measure water vapor in the atmosphere because the altimeter signals are influenced by water vapor in the atmosphere. So you need to correct for that. And following CSAT, which had a long, illustrious 13-year career, I should say that generally the Earth science satellites are designed and built to last at least 5 years. But we've been doing very well in terms of radar altimeters. So CSAT lasted for 13 years, which was great. Before CSAT was decommissioned, the Jason 1 satellite was launched. And Jason 1 just did, well, CSAT measured ocean surface topography with about a 4.2 centimeter accuracy. So from 830 miles up in the sky, it could look down at Earth and send those signals down and measure how the surface of the ocean changed, really, because it could also look at currents and stuff. So then Jason 1 came along to do the same thing and uh, had a little bit better altimeter. I think they went to the Jason altimeter, or the Poseidon. It's actually Poseidon is the name of the altimeter. Jason and Topex were joint missions with the United States and France. So the original ones were just U.S.-France collaborations. After Jason 1, then we launched Jason 2 to do exactly the same thing. Send those microwave signals down to the ocean and measure the time it takes to come back. So after Jason 2, we launched Jason 3. Now, the cool thing about launching those missions when there was still an active mission is that you could put them in the same orbit. So they would always put them in the same orbit, lagging behind the initial satellite, so that they could calibrate it and make sure that the measurement they're getting from that new satellite is the same as the one they're getting from the old satellite. So what they did with Jason 1 and Topex is after they calibrated Jason 1, they said, hey, we can move Jason 1 out of this orbit now. Let's move it over some distance away, and now we can double team the ocean. We can get measurements from both these satellites. So they did that with Jason 1 and Topex. They did that with Jason 2 and Jason 1, and then Jason 3 came along. By this time, NASA, they love to do only original stuff and one of a kind and cutting edge. So each time you launch a new satellite, you want to do something a little bit different, to prove your worth, I guess. So the altimeter, which is the primary instrument on these satellites, they were getting a little bit better and better. France always supplied the altimeter, but let's see. I think the next slide, the slide number 5, will just give you an animation to show how these altimeters work, how these satellite altimeters measure the ocean. So if we can look at that animation on slide 5. So as the satellite is moving across the Earth, it's sending out microwave signals, like thousands of them per second. And all it's doing is just going down to the surface of the ocean. They're measuring how long it takes to get back to the satellite. And because they know it's traveling, the signals are traveling at the speed of light, then they just do that little mathematical calculation and they can determine the distance. But here's the thing. When you're traveling, when that signal is traveling through the atmosphere, it's being affected by water vapor. Water vapor will slow it down or speed it up, depending upon how much water vapor there is in the atmosphere. So all of these satellites, in addition to that primary instrument, which is the altimeter, have a microwave radiometer on there. The microwave radiometer is a passive instrument, meaning it's not sending out any signals. It's only measuring the signals that is reflected, that is emitted from the ocean. So it's just up there measuring that water vapor in the atmosphere. But when they know that quantity, they can take that out of the measurement for sea surface height. So the microwave radiometer does that. Now, the other thing about all of these satellite altimeters is they also have these instruments that are called precision orbit determining instruments. So they can tell using a GPS, a laser retroreflector array, which is just an instrument that has a bunch of mirrors on it, and it's sending signal down to the ground to these stations, and measuring that distance to these ground stations. And then also an instrument called Doris, and that's a French supplied instrument. So Doris is actually a very sexy French name. Um, Doppler, it's a long word, Doppler orbitography and radio positioning by satellite, something like that. Anyway, they call it Doris. But Doris is another precision orbit determining instrument. So now we got three instruments that are telling us exactly where the satellite is on the orbit. So if you know you're making this measurement of sea surface height and you know exactly where the satellite is, that gives you a more accurate measurement. I always use the example if I was um, standing on one side of my yard and I threw a rock at this tree that's in my front yard, I could hit it from either side. Stand on the left side of the yard, stand on the right side of the tree, whatever. I could hit it, but when I know exactly where I am, that distance becomes a little bit more accurate. The measurement of that distance becomes a little more accurate. So that's what those precision orbit determining instruments do. And all of these satellites, all of these radar altimetry satellites, they have those instruments. And that's why you can get 3.3 centimeter accuracy of the measurement of sea surface height from 830 miles in space. So all of them work like that. So now we get to Sentinel-6. Sentinel-6 is the fourth JASON series. It's actually JASON CS/Sentinel. And now it's become this several partner international collaboration, because the European Union has this program called Copernicus, and within the Copernicus program, they have Sentinel, the Sentinel series of satellites. So, we're on Sentinel-6 now. So they've been launching Sentinels for a while. I think Sentinel-2 maybe had a radar altimeter on board as well. But Sentinel-6 is a two identical satellites. They're launching about 5 years apart. And the reason for that is, again, you want to continue making the same measurement. I was taught that you can only monitor something if you can measure it. And the better your measurement and the longer time that you measure, now you can begin to monitor. So with Sentinel-6, actually with the JASON-3, JASON-2, and JASON-1, we are now monitoring sea surface height using these satellite radar altimeters. So I'm at slide 8 now, because I mentioned that Sentinel-6 is two identical satellites. They were known as Sentinel-6A and Sentinel-6B. They were going to be launched 5 years apart. Well, in January of I want to give it some fancy name, 2020, the year of I don't know, what's the worst thing you can think of, I guess, the year of that. But in January of 2020, the Europeans, the Americans, all got together and decided that they wanted to change the name of Sentinel-6A and name it in honor of Dr. Michael Freilich, who was the director of NASA's Earth Science Division. He actually, I think he started his career at JPL. After he left JPL, he went to University of Oregon or Oregon State, one of those Oregon colleges, and he was a dean up there or something. But really, really cool dude, really passionate about understanding our planet, and not just, you'll see something later on, is not just, the US studying our planet, or the French studying our planet, or Europeans or Africans, or, but that this was something that we all needed to do together. to understand how our planet works. So they named Sentinel 6A, now called Sentinel 6 Michael Freilich. And so now I'm at slide 9. We just, if you look at that, there is this series of satellites now starting from Topex, coming to Jason 1, Jason 2, and then Jason 3, and Jason CS. And the CS, by the way, stands for Continuity of Service. So now this is an operational satellite. The Jason series is operational. That means that NASA doesn't do operations. NASA does cutting edge stuff. So now the operation of these satellites is turned over to NOAA, the National Oceanic and Atmospheric Administration, because that's what NOAA does. NOAA does operational oceanography. So as I mentioned, this long-term record of sea surface height has allowed us to see how the ocean has changed. The ocean surface or sea level has changed over these past like 28 years or so. And if you look at slide 10, you'll see that these satellites have been measuring an acceleration in sea level rise. And it's not a good thing. I mean, it's really not a good thing, especially if you live near the coast. But we're measuring it globally. So even though we can say that global sea level has risen, you know, 4 or 5 centimeters in the past 20 years, the more important thing is what is regional sea level doing. So if you look at slide 12, oh, and you might have noticed that there was a dire prediction about 2050 if the acceleration rate continued as it was or continues as it is. Sea level, it will end up over 240 centimeters, I think it was there. But what's happening regionally? What's happening in Southern California? We're close to the ocean. If you look at that chart, it's only less than two centimeters. Is it centimeters or millimeters? I gotta put my glasses. I got my glasses on, but I need to look at. Okay, yeah, less than 2 centimeters for Los Angeles. But if you look on the other side of the world, so like the Western Pacific Ocean, Sydney, Australia, has seen a regional sea level change of 15.2 centimeters. Now that's a lot over that period of time. That's a lot of water. So, but it's important to measure and monitor sea level change. And we can see what's happening. We know that sea level has really 2 components. It can be caused by thermal expansion, which is what the altimeters measure, because they're measuring height. They're measuring how high the water is. But also, when you start melting the ice, then that's adding volume to the water. So those 2 components are what make up sea level rise. So the altimeters measure the thermal expansion very well. And we also have a satellite, which I'm not talking about, GRACE, Gravity Recovery and Climate Experiment, which measures very well how sea level is affected by volume increases. So it's measuring the mass of ice sheets and glaciers and stuff and seeing them change. Okay. So the slide, I guess I'm on slide 13 now. Did I skip something? Let me see. On slide 13. So those are measurements of carbon dioxide, and then on the right, measurements of global sea level rise as measured by these radar altimeters. And then they look awfully similar. So this is like I think Josh Willis calls this his canary. This increase in carbon dioxide is what's warming the earth, but that heat, that excess heat, is going into the ocean and it's causing sea levels to rise. So we're measuring and monitoring sea level. But like I said, now we've been doing this for 28 years. We ought to know what we're doing. And so NOAA and other operational users, UMETSAT, which is the operational arm of the European uh, community that that operates these satellites, they are um, bringing bringing to the forefront several operational uses of these data. One important one in slide 15 is climate research, because we know now that the excess carbon dioxide is changing the climate. So we can use the information that we get about sea surface height, sea level rise, to help us understand the climate. And also some other operational uses on slide 16, improved weather forecasts. So we can use sea surface height because it also tells us something about the heat in the ocean. Um, we can use that information to help us understand storms and how storms are moving across the ocean. Um, Improved hurricane forecasts. Scientists know that a hurricane is fueled by heat in the upper part of the ocean. And more importantly, deep down heat. And that's dangerous when you got heat deep in the ocean, not just on the surface. And that's what turns those hurricanes in the Gulf from, you know, category 2 to category 5 overnight. They pass over a warm pool of water. And then another thing is the El Nino and La Nina forecast, which Topex kind of made that a household name, El Nino and La Nina, because these satellites are measuring the height of the ocean. Warm water will be higher, and we can see on the satellite data the warm pool of water, which is characteristic of El Nino, a warm pool of water moving from the east to the west in the Pacific Ocean along the equator. Um, and for us here in Southern California, El Nino's got some good things and some bad things. Surfers love it because it creates some nice big waves for them. But when you have rain for 40 days and 40 nights, that's not so cool for someone who lives on the side of a hill, you know. So but El Nino, it not only affects weather in the Pacific Ocean, but because the Pacific is so large, it affects the weather across the globe. So the El Nino forecast is something that they're using the data operationally to help with. Um, uh, Oil spill response. You can track where the oil spill goes using the satellite radar altimeters. You can do search and rescue because you can tell, like somebody falls off a boat, you can tell which way the currents are moving. That was actually, that was probably the biggest thing that the scientists wanted to use this satellite data for, is to understand how currents move around the earth and how they transport heat from one place to another, so that you can use that same principle to find out where somebody might end up when they fall off the boat in, I don't know, Catalina. You know, so you could use that. So those are all operational uses. Government agencies, private industries, um, uh, sailing enthusiasts, they can all use these data to help them do what they do. Now, for Sentinel-6 Michael Freilich, I put a little note on there that says, keeping the good going and making the good better. And that's because we have now, for the Sentinel-6 Michael Freilich spacecraft, the radiometer, the microwave radiometer. Remember, I said they all have them, but now it's It's called the AMRC, for Advanced Microwave Radiometer for Climate. In addition to that AMR, there is um, an experimental high resolution microwave radiometer. The idea is when you use the radar altimeter, once it was great over the open ocean, but once you got close to the coast, the data were junky. The scientists who developed the advanced microwave radiometer, he explained it to say by saying that when you got to the coast, the altimeter didn't know if it was looking at land or, I mean, well, the altimeter did it because but the radiometer didn't know if what it was seeing was an effect of land or an effect of the water. And so he called it being blinded by the glow of the land. And they wanted to correct for that. So this new experimental HRMR, high resolution microwave radiometer, the idea was to get the resolution better so that you can actually get good data as you cross into the coastline, good altimeter data as you cross to the coastline. Another experiment on Sentinel-6 microfilate is the GNSSRO, which is Global Navigation Satellite System Radio Occultation. And that instrument, it's looking at GPS satellites, it's looking at global navigation satellite system satellites, and using that information to determine what the atmosphere looks like, different layers of the atmosphere, because as the satellite goes across the limb of the Earth, then you get that the signals are changed by the atmosphere. So they're using that to understand and help with weather forecasting and just help understand the atmosphere better. Let's see, what else do we got on here? There's that Doris again, of course, that French instrument, the laser retroreflector array. There it is again. So all of these same, it's like if it's not broke, don't fix it. And if you could make it better, do that. So that's what these instruments are doing. Okay, I'm gonna go on to slide 19, which is you've seen all of these applications already because Topex did them. This measuring global sea level, the real-time surface currents, the El Nino, La Nina, ocean heat content, and tropical cyclones. They've all done this. So Sentinel-6 is going to continue keeping the good going, but also making the good even better. So there's that next slide, 20, talks about how the HRMR works. It's got 3 frequencies that it's using, and they're much higher frequencies than the regular advanced microwave radiometer. So, but they use the same reflector, and it's going to be helping. It's going to be helping. Okay, so let's go on to slide 21, and that describes the radio occultation experiment on Sentinel-6 microfilate. So it measures the phase delay of that signal of the global navigation satellite system signal as the signal goes through the atmosphere, the different layers of the atmosphere. And then the algorithm that collects the data, it converts the phase delay of that signal to bending angle profiles from whence they get the refractivity, temperature, and humidity at the tangent point of where that signal crosses the atmosphere. So that's very helpful in terms of understanding weather and climate, and also improving the forecast thereof. So We talk about Topex, Jason, and the era of modern altimetry, which is with this fancy uh, microwave radiometer. We're now using the Poseidon 4 altimeter, which means that we Topex, I think they just called. Um, I don't even think they called it Poseidon 1. They just called it Poseidon altimeter. But that altimeter has been improving with each satellite. Okay, and then you'll see on there. So you have Sentinel 6A, Sentinel 6 microfilament, and Sentinel 6B. But right in the middle of those is something called SWOT, Surface Water and Ocean Topography. And SWOT is is like next generation kind of radar altimetry, because SWOT is going to use radar interferometry, which means that you have two antennas and they are measuring the same area, and you measure the difference between those two measurements. And so now with SWOT, not only are we going to be looking at the ocean, we can look at surface water, measuring lakes and rivers and the flow rate of a river and the depth of those lakes and stuff. So that's very exciting work for these two scientific communities, the oceanographers and the hydrologists. So SWOT should be launching in 2022, so not that far off. But if you were around a few months ago, we would have said it was launching in 2021. So things change. I don't think I've ever seen a mission launch when it said it was going to launch. Um, and as an outreach person, we make products, so we're forever making products, spending money, and then deciding, this is not right anymore. It was supposed to launch in 2021, so we can't say that now. But it's still very, very cool stuff. If you look there at slide 24, it shows you the SWOT payload. So, and you will notice that there's that Doris, there's that laser retroreflector array, there's that microwave radiometer, and the nadir altimeter. But now we got something called a Ka band radar interferometer, and that's what's on the ends. This instrument, if you look up at that, well, I guess right to the right of that, you see those two long arms coming out the side of the spacecraft bus. Those are the radar, the Karen, the radar interferometers, and that gives you much higher resolution. So now, I think I have in slide 25, there is an animation that shows you how SWOT will improve the resolution of these radar altimeters. So if you could run that animation, that'd be great. You see a little bar go across the bottom of it. And actually, that one went way back to GeoSat, which was not a NASA spacecraft, but it had an altimeter on it as well. Okay. All right. So one other thing I wanted to say about the reason that we need to monitor these things is I liken it to if you go to the doctor, say you go to the doctor today, uh, January 13th, 2021, and you go and the doctor says, "Oh my God, you're so healthy. Your weight is good. Your blood pressure is good. Your cholesterol is good." And you say, "Great." And then the doctor doesn't see you for another year. You go back January 13th, 2022, and your weight is good and your blood pressure is good your temperature is normal. But what that doesn't show you, because there are only 2 points there, what it doesn't show you is that uh, in November of 2020, man, you had the flu and you were sick and you felt horrible and terrible, but the doctor can't tell that. Well, it's the same with monitoring Earth. You can't tell if you have one, you have a satellite for 5 years, you don't see what happens in 10 years. Because Topex lasted so long, we discovered things happening to the ocean that you would not have seen. We discovered that El Nino, La Nina, those kind of features happen every 3 to 7 years. And uh, then because we continue the monitoring with Jason 2, Jason 3, there's now they talk about Pacific decadal oscillation, where the Pacific Ocean changes from one state from a negative phase to a positive phase. But we would have never seen that had we not had this continuous monitoring of the ocean with these radar altimeter satellites. So Sentinel-6 Michael Freilich is just the next in that series of looking at and understanding our home planet, not just for us, but for the benefit of all of us, not just for Americans, not just for the French, for the benefit of all of us. And it's important to look at Earth as a system, not just these disconnected kind of scientific disciplines, but look at it as a system, because obviously the atmosphere is affecting the ocean. Obviously, the ocean is affecting the land. So we need to look at it as a system. And that's the cool thing about using space. It gives you a unique vantage point to do all these things. We can measure things over and over and over again. The satellites don't take vacation. They don't take Christmas break or spring break or any of that stuff. They just keep doing what they're doing. And for that, we are grateful. So what I wanted to leave you with is just a little bit from Mike Freilich. Mike Freilich passed away in August 2020 from pancreatic cancer. So it was really a blessing that the satellite was named after him, and he got to be, he got to witness the satellite being named for him. Unfortunately, he did not get to witness the launch, but his children were at the launch. So his legacy lives on, just as the legacy of Topex Poseidon does. So if we could just roll that little bit of video.
My story is likely quite atypical. I knew in 10th grade that I wanted to be a nearshore oceanographer. What has driven me is understanding how nature works.
And that's why humanity, not one agency, not one country, not one continent, but why humanity has been monitoring global sea level from space with exquisite accuracy for more than 28 years.
I'm very pleased to rename Sentinel-6A in the future to be called Sentinel-6 Michael Freilich.
Earth system science is bigger than any particular agency. It's bigger than any single nation. It's bigger than any single continent. And I surely hope, because humanity requires it, that we make some significant progress in understanding.
You did good, Dr. Freilich, for all of us. And for that, we're all very grateful.
And as the scientist said, she said, "You done good, Mike Freilich." And we can say that our satellites have done good, and we just trust that they will continue to do good, studying our home planet. Right? Thank you all very much.
Awesome. Thank you so much, Annie, for sharing all this. I mean, I learned a ton. I think you really already answered so many questions that we had submitted online. A lot of people, like Ella was asking, about how these missions have evolved over time, and being able to understand just that, this dramatic increase in resolution over the last few decades. It's incredible. My buddy Kamani was asking, why do we need so many of these in the first place, right? Why do we need so many satellites? And being able to see that continuity, I think, is really incredible. I was wondering too, as we see some people asking about like kind of the quantity and diversity of these missions, how is it that other missions that are looking at orthogonal modes of detection, right? Not just kind of the next JSON or anything like that, but does Earth as a research kind of organization at JPL and NASA communicate across looking at temperature versus sea level height versus greenhouse gases? What does that collaboration look like?
Well, yeah, that's good, because that's very important. What you will find in the earth science community is one scientist is looking specifically at sea surface height, but he's discovering that, well, in order to understand this, you need somebody to come in and tell him what the ice is doing. So they work very closely together to solve problems. You might take one portion of the problem, and I might take another portion of the problem, but the goal is to get the problem solved, to understand Earth as a system. So maybe you're in your cubby hole and I'm in my cubby hole, but there's somebody, probably our manager or something, that's bringing us together.
We have a ton of questions, including we got DJ's class watching. A lot of questions about global warming and climate change and what they can do to stop it. Are there steps that young people can take to kind of begin making an impact?
What I always say is, you do what you as an individual can do to reduce your carbon footprint, to live more sustainably. I mean, I'm not giving up the meat yet, but I try to not run the water so much, take a quicker shower, not drive when I don't have to drive. Well, it's things like that. It's the little recycle. If you're going to use a plastic bottle, the better thing to do is fill your reusable bottle up. But if you're going to use a plastic bottle, recycle it. Don't throw it away. Recycle it, and think along those lines with everything you do. I always ask students, well, how'd you get to? Well, back in the day when people did go to school, how'd you get to school? Did you walk to school, or did you drive to school? Did your parents drive you to school? Did you pick up anybody else? Or did your friend come with their parents too, and everybody gets dropped off? Well, those kinds of things. If you live down the street from me and we're going to the same school, sometimes it's difficult, obviously, because my mom got to be at work at 7 o'clock, and your mom doesn't have to be at work till 8 o'clock, and we got to be at school at 7:30. So my mom she's got to do it. But it's the little things. It's the little things that we can all do.
Yeah, it was interesting. We were talking in this morning session about how more and more schools are kind of implementing some of these solutions, like not using disposable silverware. And in fact, just recently I ordered some food, and I saw on the website you could click a box that said, don't include the disposable silverware. I have my own silverware. And I thought, absolutely, why not? So really, I mean, very, very little steps, and can really seem to add up to a big impact.
Right. I think we're like 6 billion on the planet, 7-8 billion. If we all do a little bit, even in America, we got 330 million, right? If we all do a little bit, and it's just, being conscious of what we're doing and thinking, well, let me do this differently now, because I know sea level is rising and I don't want to drown. So,
Kind of in a similar vein, actually, someone was asking. You showed a slide where sea level was rising at different degrees for different places. So this kind of idea of where is it dangerous to be, and what does that forecast look like? Can you comment on why is it not rising evenly, and when do we need to be worried?
I think it's always not rising evenly. When what the satellites are doing is getting a global perspective. Um, some parts of the world are higher than other parts, so it'll take sea level longer to catch up to them. There's also this thing about subsidence. The land is actually subsiding, which gives you relative sea level rise there. There are places on the East Coast where they're having now, they call it nuisance flooding. So not maybe a short rain or something, and the streets flood, and it didn't used to happen. So they're seeing the effects locally of global sea level rise or regional sea level rise. And I mean, there was an article recently, it may have been on the Sentinel-6 website, where we're talking about the NASA assets that are in danger. Because all the launches happen from the East Coast on the water or from the West Coast on the water. And those assets are becoming I don't want to say endangered. What's the word I want to use? Threatened by sea level rise. You cannot have launches with water, coming up to the rockets and stuff. So they're looking at those things. They're moving like buildings up to higher ground, for example. So even though some people would say that it's not a big deal, it's a hoax, climate change is a hoax, we're seeing it. We're seeing the effects now. There are island nations that, 10 years ago were starting to be affected by sea level rise. And what do? About 70% of people live near the coast. So 70% of the people could be in trouble come 2050 or whatever that year was, where he talked about sea level having risen so much by that point.
Yeah, I think it's really wild to think about how different geographies respond to this differently. You mentioned this nuisance flooding on the East Coast, or perhaps an island community. In California, this is a huge problem for us, where we are such a powerhouse for agriculture, right? So you mentioned ground subsidence, which reminded me about this impact on watering and farming and providing food for the United States. Obviously, climate change is going to have a really, really strong adverse effect on that.
Yeah. Oh, now there's something I didn't mention, because it's not just sea level rise. There's also a phenomenon called saltwater intrusion. So as sea level rises, and the salt water gets into the freshwater table, we can't drink the salt water. So if our drinking water is contaminated, we're in big trouble, especially here. I mean, we don't have much water here anyway. We really shouldn't all be here in Southern California.
Yeah, whenever I see a fire or an earthquake, I certainly agree. But the weather right now reminds me otherwise, at least. Maybe one last question. A couple students are asking, what happens to these satellites when they're out of commission? Where do they go, and how do we kind of keep a room for them, right? Keep space free from space debris.
Okay, and in terms of the Topex Jason series of satellites, what they will do is, once the satellite stops working and is decommissioned, I mean, nobody's going up there to put a lasso on it and bring it back down. But what they do is they make sure that they have enough fuel so that they can move the spacecraft to a parking orbit, it's called, and it'll just be up there I mean, you could still go out and see CSAT on a, you have to go to the desert or someplace clear, but they're just up there, and they become so much space junk. Yeah.
Well, we're running out of time. I want to thank you so much for spending your final few days at JPL with us. Really appreciate taking the time to put this together and do all this setup work. So thank you so much. I really learned a ton. I hope everyone watching did as well. To close out, I wanted to show you guys just a few slides about what JPL education can offer as well. So if you see on the screen now on my first slide, I encourage you to go to this site, jpl.nasa.gov/edu, where you can find just a plethora of resources around classroom materials to talk about climate, either with your friends, your family, your students. Really some incredible stuff. On the second slide, you'll see we have activities for all age groups. So this one here, precipitation towers. You can see me being swarmed by a horde of kids as we look at just rainfall patterns in different cities. Much like Annie mentioned, don't give them Pasadena. That's a too easy. There's really no rainfall to measure. But you can see seasonality as we look at different geographies. On slide 3, you'll see kind of the next version up of this. So this is a lesson put together by a really great teacher, looking at the GRACE data that you heard Annie mention just briefly. So how are we looking at how gravity changes and how that correlates to sea level rise? So kind of some more advanced data here, some really neat way to kind of tier this for different grades. On slide 4, you'll see that this extends not just to our oceans, but to our Earth as well. So we love, and I have been a recent convert to the miracle of geology and understanding better our Earth science and how important that is. I've learned now that this is really just like chemistry, my passion. It's just a lot slower. Geology is just slow chemistry, but we have activities there as well. So I encourage you guys to take a look at, something that'll give you perspective for our Earth and this concept of geological time. So, we look at this data and we're not talking about 5 years or 10 years. We're talking about stringing together trends over our Earth's life. And there's some really interesting activities there. On slide 5, you'll see a site that got mentioned several times, and this really should be our starting point. So climate.nasa.gov is where you're going to find all of these resources in one place. I personally find this site very important for talking to my peers, perhaps people that are not scientists, but are kind of trying to understand better what climate change is and how we know that it is real. This is a place to kind of get the data as it comes from these scientific missions. You can see at the bottom of the figure there's this kind of like arrows. I call this like Earth's pulse. By clicking on these, you can see how we're tracking these different facets of climate change and how the trends have kind of lined up over time. On slide 6, you'll see that, again, this is really just a sample of many of the things we have. So the news section is a great place to just kind of educate yourself on what's going on at NASA, what's going on in climate change, as well as, of course, everything else that NASA is doing, like exploring the solar system. But this is kind of a good place to start and get your background knowledge and filter through. If you are a teacher, slide 7, it shows the Teach website, and these are activities that my colleagues and I have put together in earth science and all topics in STEM. And this is where you can find next generation science standards aligned lessons, filterable by grade, filterable by topic, so that you can really get to a 5E lesson planned activity very quickly to hopefully bring this type of material to your kids. As you heard Annie talk about, we're really trying to get the next generation to understand the impact that they can make, so that hopefully we can course correct and treat our planet better. If you are looking for a section that's not so teacher-centric, slide 8 shows what we call the Learn section. And these are activities that are kind of written for you as students or just people of generally interested to kind of go through step by step. So, you know, things that if you want to take a look at and you want to learn about, here are some activities that we've kind of modeled for you to be the self-driven learner. So on slide 9, you'll see that we have really some great collections of all of these activities in a single place. This is a learning space. We have a corresponding one, teaching space. And these places, just like climate.nasa.gov or the general education website, are going to be you know, more than enough for you guys to dig through. And if that's not enough, then on this final slide, you'll see that these resources extend, you know, well past the classroom, beyond grade level. So articles, videos, data, everything you could hope for is here. And I hope you guys will take a look at this, take this to your classrooms, take this to your kids and your students, because they are really our best hope, and we are relying on them to kind of carry the torch and keep our planet safe going forward. So with that, I'll close out. I want to thank you guys so much for spending the last hour with us. I hope you enjoyed, and we're really excited to talk about earth science with you. Please check out the education website and the climate website if you have any questions, and it's really easy to get in touch with us if you'd like to discuss more. So thank you guys so much. I hope you enjoy the rest of your day, and looking forward to seeing you next time.